Hi, I'm Damilare, presenting on a computational study on unsteady aerodynamic forces around a pitching airfoil with shock and shock-induced separation, being a conference paper written by Damilare and Hirosita from Division of Mechanical and Aerospace Engineering, Hokkaido University, Japan. This is my presentation outline and to the background. Some of the requirements of modern commercial aircraft include structural flexibility and ability to operate at transonic flight speed, and this often subject them to a phenomenon of aeroelasticity. So I would like to talk a bit about it. Aeroelasticity is a phenomenon that involves the combined effects of aerodynamic forces, elastic forces, and inertial forces on this flexible structural aircraft structure due to relative motion of the surrounding fluids. We have various types or different categories of aeroelasticity, but I'll be limiting my talk to flutter because it has a far-reaching effect among all aeroelasticity phenomena. Flutter is self-excited vibration in which aircraft wing vibrate at natural frequency due to flow instabilities, as it can be seen in this movie. It involves fluid force and structural force. Here, the aerodynamic force feeds energy to wing structure with each vibration cycle. And as such, when there is insufficient overall damping, the amplitude of vibration tends to increase with the number of cycles of vibration, and then later leads to a catastrophic failure of the wing structure. As it can be seen, when these three forces interacting, and it leads to a dynamic instability. This dynamic instability leads to fouling oscillation that leads to destructions of aircraft wing or aircraft structure. This is a non-desirous phenomenon that must be prevented. In order to talk more about this phenomenon, there is a need to discuss about flutter curve, and here it's a plot of velocity against Mach number, in which a linear theory can be seen here. Below this is region of stability, and above this line is point of instability. But at free stream Mach number, transonic Mach number, it can be seen that there is a little bit deviation from a linear theory, and this portion is referred to as a transonic dip. Transonic dip is actually associated with non-linear flow features like shock waves and shock wave boundary layer interaction, which often leads to non-linear wing response. As it can be seen from this simulation, this airfoil is being simulated in a transonic flow speed, and we can see the appearance and disappearance of shock wave on the upper and the lower surface of the airfoil. This is often increases the aerodynamic unsteadiness. When this happens, linear perturbation theory can actually capture this region. So it's very important to carry out intensive study in this particular area by considering the effect or the role of shock wave and shock induced separation. Why? Because this particular curve is very important, and it actually determines safe line conditions. Therefore, the role played by shock wave and shock induced separation in an unsteady aerodynamics needed to be critically studied, which is the major part of this work. So the purpose of this work is to pay particular attention to the role of shock and shock-induced boundary layer separation by making use of a forced oscillating airfoil in a transonic flow. Now, the numerical method used involves compressive Navier-Stokes equation as the governing equation. Right? The time integral method used is LU-SGS implicit method, and the numerical flux is choose using MOXO, and the turbulence model is SA. Which now computational setup. The data from NASA is used and compared. So from there, airfoil use for the computation based on the experimental work is NACA 64A010, operating at Mach number 0.8 and Reynolds number 1.2 times 10 to the power 7 at a reduced frequency 0.2. The mean angle of attack vary from 0 to 6. 0 and 4 actually provided in the experimental data. 2 and 4 is the new included angle of attack, mean angle of attack, and the amplitude of pitching is at 1 degree. Now this equation shows the relation for reduced frequency, where omega is the angular speed, c is the chord length, and u infinity is for means free stream velocity. And this second equation is equation used to determine the instantaneous angle of attack for mean angle of attack with amplitude of vibration 1 degree. The grid setup includes the following. The grid resolution is 399 by 100. The grid topology is O grid. The external boundary is 20C, and the minimum grid width is 2.0 times 10 to the power minus 6. C in these expressions refers to the chord length. Now, in order to validate this particular work, comparison between numerical analysis and experimental data were carried out. For the mild angle of attack, recent study by Wexin was actually compared with this present study, and for the high angle of attack, experimental data from NASA was used. And this is for the main angle of attack 0 degree, which is taken for the mild angle of attack. A plot of CL, coefficient of lift against angle of attack and coefficient of moment against angle of attack were plotted, and it can be seen from here that there is a perfect agreement in the plot of CL against AOA. A little bit disparity for CM against AOA, and it's due to the fact that unsteady aerodynamic is more evident in the coefficient of moment than that of coefficient of lift. This animation shows the appearance and disappearance of shock wave on both upper and lower surface of the airfoil. And from here it can be concluded that at mild angle of attack there is a good agreement between the work done by Wexin et al. This present study, and the shock wave is actually captured correctly. And for the high angle of attack of mean angle of attack 4 degrees, DFT analysis was performed, as it can be seen from here, and the result is compared with the experimental data from NASA. This part is for the real part, and this is for the imaginary part. A good agreement can actually be seen from this plot, from this graph. This is a movie. This is a simulation showing the movement of shock wave and the separation region. Then this also shows that this present study have a good agreement with experimental data, and also predicts the behavior of shock wave and separation accurately. Then the grid that was used for the comparison study was put into grid convergence test, and 3 grids were used, and it can be concluded that grid B and grid C actually converge. And in order for to save computational cost, grid B was chosen for this analysis. And from the previous slide, it has been proved that grid B accurately captured shock wave dominant at mild angle of attack and the dominant of separation at higher angle of attack. For further analysis, effect of changing the mean angle of attack on unsteady aerodynamics was actually performed, and the mean angle of attack is varied between 0 to 6. This diagram illustrates the important parameters, as this shows the mean angle of attack and this pitching at quarter chord point. So the reason for doing this is to determine which of the shock wave and shock-induced separation dominate either of mild or higher angle of attack. So let's find out. Now this slide shows the marked distribution along various mean angle of attack. This is for 0 degree, and as it can be seen, there is appearance and disappearance of shock wave both on the upper and lower surface of the airfoil. For 2 degrees, we can see that we only have the shock wave being developed at the upper surface with less or mild separation occurrence. Now at 4 degrees, there is wider movement of shock wave at the upper surface with more separation taking place. While at 6 degrees, we have the same scenario, such that the movement of the shock wave is wider, and also we have a more induced separation. For the start, a plot of CL against angle of attack is made for the static case, and from this a kind of corresponding trend can be seen from lower angle of attack, that is from -1 to 2 degree angle of attack. Why after the 2 degree, a kind of deviation in the changes of CL against angle of attack can be seen, and as it can be seen from this graph, it's illustrated that shock wave actually dominate this region. When there is addition of shock separation, it causes a slight deviation, and when it is massive, we can see a further deviation from what we have at this region. So that is what we are trying to find out in this slide. This is a plot of dynamic case. As we can see, at mean angle of attack 0, we have shock wave from this simulation appearing and disappearing on the both upper and lower surface, and we have a kind of anti-clockwise flow direction. The same thing can be seen for mean angle of attack 2 degree, but when we get to 4 degree, there is a slight change. There is a change in the direction, and as we can see from this simulation of higher angle of attack of 4 degree, we can see the effect of separation, which causes a wider movement of shock wave and tends to reverse the direction of flow. So typically at this stage, we can say for the lower angle of attack, which shows a normal trend, can be regarded as a typical phase delay, while at 2 can be seen as a kind of transition phase to phase advance. Now we go further to plot static and dynamic case together and trying to find phase difference, find the phase difference between the two cases. I won't talk. I would like us to see what we have here and compare with what we have here, and so on like this. It can be seen that this mean angle of attack 0 show a kind of normal trend, which is expected. For a lower angle of attack, it's seen that for the steady case, it shows a lower value compared to dynamic, but at higher angle of attack, as is expected, we have higher value for the steady, for the static case, and for the dynamic case, it's lower. But we have a different trend when we compare with 4 angle of attack. Now we can see for 1 degree angle of attack, this one compared with mean angle of attack 0 and mean angle of attack 2. From this CP distribution, we can see the dotted red line signify the static case, and the blue is for main angle of attack 0 and the green is main angle of attack 2 degree, all at instantaneous angle of attack 1 degree. It can be observed that there is difference between the fallow, which is normal at this stage. When we move to main angle of attack 2 degree, it seems that we have the same fallow for static and dynamic case. It shows a kind of a transition, a kind of change in the flow and the fallows of CL against angle of attack. So now if we now compare this region and this region with what we have this region, we can see that there is a kind of a change in the scenario, such that the static case at lower angle seems to be higher, whereas it's lower here. And when we move to this place, it showed that the angle of attack here is for static is lower, and that of dynamic is higher, unlike what we have at main angle of attack 0 degree. This is as a result of the influence of shock wave separation, which cause wider range of shock wave and causes a kind of reverse in the flow direction. And from this, it can be concluded that the unsteady aerodynamics around a force oscillating airfoil in a transonic flow was fully investigated, and that SA is good enough for the prediction of unsteady aerodynamics, and that at mild angle of attack, especially angle of attack 0 degree, is being dominated by shock wave. But at high angle of attack, it's being dominated by shock wave and the appearance of separation, and thus we have a typical phase delay, transition phase, and advanced phase. Thanks for listening.